we're going to make a start from the gradient of a straight line. Now the gradient is also called a slope, also called the rate of change, and so on. And as you might remember, it's rise over run. Now if you have 2 points here, the rise is just this part, and the run is just this part here. So rise is y2 minus y1, run is x2 minus x1, and you do that and you see what the increase in y is for an increase in x. This works perfectly for a straight line. You don't need to bother with complicated formulas or anything. So just to make things a bit clearer, instantaneous gradients are a tiny gradient. I'm just going to try and draw this out. You see that it's getting less steep as you go towards the positive x side, and it reaches 0 at this point. And non-zero is at this point, but between these points you have a negative part that goes like this. So these are all tiny slopes, and each of these slopes will have different values. My drawing isn't the best, so but you can still pretty much see that it's very steep here, and then it's sort of 0 around this mark, and then it's negative, 0 here, positive. What I'm trying to get you to understand from this is that the gradient is changing for every single point. You should remember this from before, that a line like this has a positive slope, a line like this is a 0 slope, and a line like this is a negative slope. So this curve has a combination of all these lines, meaning that it has a combination of different gradients. So in order to find the derivative, you would need a mathematical equation with an x. So whenever you plug in an x value, you get a different gradient corresponding to the curve. So basically, building up from what we've learned so far, have a look at this curve. You can see that it's very steep here, and then getting less and less steeper as you go and reach 0 right about here. That's your 0, and then it's sort of moving towards the positive side and becoming more steeper as you go. So if you were to put numerical values here, this would be highly positive. This would be highly negative. And then it's moderate here and here. And then it's 0 around here. This corresponds to the 0 point here, this curve. That means whenever you have a turning point, it's going to be a 0 on the derivative equation. This is our derivative equation. So if you plug in any values here, that will give you the derivative or the gradient for this curve, the blue curve. So if we were to do the instantaneous gradient here, you'll see that starting off less steep and sort of following the shape through, getting steeper as you go along. If you were to fill in the gaps between the dashed line, it would look almost identical to the actual curve, and this is what you have here. So that's why the derivative of e to the power x is again e to the power x. Now I am going to go through this derivative function to a bit of detail. Let's identify the maximum and minimum points in the first curve. So your first maximum point is here, first minimum point is here, second maximum point is here, and the second minimum point is here. Now the questions might ask you to do a gradient graph when you have a cyclic function like this. This is the best place to start. So you identify the maximum and minimum points, and you'll see that those points correspond to zeros on the gradient curve. So you see you have a 0 here, a 0 here, a 0 here, and a 0 here. So 4 zeros for 4 turning points. Now, from here to here, it's positive, going from steep to less steep. So it's going from a high positive value to eventually 0. And you can see that here, it's starting off at, say, a high value at 2, and then going down to 0. And then you can see that it goes negative and then to 0 again. You'll see that's the case with the gradient as well. So hopefully you're getting the hang of this. And then, the same thing follows here, and then you read 0, and you can see that in this curve as well. So that's how the gradient curve works, and this is how you can generate a gradient curve of a cyclic function.